Hello and welcome to my channel. So this is my first video and I'm just gonna get started real easy by doing a COMSOL tutorial step by step that is actually straight off of the COMSOL website. So let's bring up the here we go. I'm going to have the COMSOL tutorial on one side, and there we go, half and half. All right, so let's see. Nope. There we go. All right, so you should be seeing on the right hand side, this is the COMSOL tutorial for flow past a cylinder, and this is on COMSOL Multiphysics version 6.0. And this is what the end result will look like, hopefully, following their instructions. So we're going to get started with modeling. Okay, they do provide a multiphysics file, the MPH file, with the geometry already completed, but I'm going to go ahead and do it from scratch since this is the tutorial video. So from the start, we're going to select Model Wizard, this top one here. In the Model Wizard window, click 2D. Okay, so two-dimensional model, and the select physics tree, select fluid flow. Here's the fluid flow and single phase flow, and under that select laminar flow, SPM. Alright, and it gives you a little description about what you're selecting here. So we're going to click add, and you'll see it pop up in the added physics interfaces, and then select study. Okay, and then done. Oh, I didn't choose time dependent. Let's go back. Well, that's all right. We can still do it from here. So under study, I'll do add study, time dependent, and add. So if you skip a step like I did on accident here in the tutorial, you can always do it from the main page. Alright, so here on the left hand side, you'll see the Model Builder tab, then we have Settings, and then the Graphics window. So first thing we're going to do is define global definitions for parameters 1 in the Model Builder window. Under global definitions, so that's this first one here. I haven't titled it. I guess I should go ahead and save it. And just, let's do let's call it flow past a cylinder. Alright, so I need let's do a new folder for COMSOL. Okay. Put it in a folder you can easily find, and I'm just going to call this flow past cylinder. Alright, so in the Model Builder, under Global Definitions, click Parameters 1. In the Settings window for Parameters, locate the Parameter section, and in the table, enter the following. So I think this is also included in the file. If you upload the file they provide on COMSOL.com in their library, you can just upload all these values, but we'll enter them manually. So so the first column in this table is the name of your variable. You can call it whatever you want. That's how we'll refer to it for the rest of the references. Expression, you'll write the value, and then in brackets, put the units. So here it's 1 meter per second is the value. Let's see, this is, there we go, it's a little better. And then that'll carry over into the value section. So you can't edit value, you can only edit expression. And then in description, we call this mean inflow velocity. I have my little space heater on behind me, so I hope it's not picking up too much noise on my mic right now. Alright, and then H, 0.41 meters, and that is the height. W for width is 2.2 meters. And you can enter these into the geometry itself, but the issue becomes if you reference it in more than one place, or if at some point you want to change it. It's much easier to just have all the variables in the same table under parameters 1 in your global definition section. So the cylinder radius is 5/100ths of a meter. Okay, next create a smooth step function that you will use for ramping up the inflow velocity. So step 1, in the home toolbar, click f of x functions. So here's our home toolbar, and you've got all of these tabs here, and we're looking for this one. And the nice thing about their tutorials is they give you an actual icon that you're looking for. So here's the f of x function button, and choose global. So these are the global and step. So here's step. In the location text field, or in the settings window for step, locate the parameter section. So here's the parameter section. In the location text field, type 0.05. So we're just telling it where to locate this geometry, or this step in this case. Okay, now we're on to geometry. So in the geometry, for rectangle 1 in the geometry toolbar, so we'll click on geometry here, the third tab over, click rectangle. Oh, that was square. This is square. Undo, undo. Alright, so for undo, I'm just doing Control and Z. It's the same keystrokes as if you're in Word or any other GUI. Okay, so rectangle, and in the settings window for rectangle, locate the size and shape. So here's our size and shape section, and the width, type W. So here's where I was talking about, you could just type in the numerical value that we entered in the global parameters or global definitions. And height, we'll put H. So if you were to say, this is especially convenient if you had a multiple of some variable. So you could say width and height are set as, 2 times, the height will always be 2 times the width. 2 times width. And that way you only have to change the variable in one place, and your scaling stays the same. But we'll say W and H, since that's how we define the variables. Click build selected. So we're looking for this icon here, and it's actually right here in the settings. Build selected, and you'll see rectangle of the dimensions that we defined at the first step. And where you locate it, it's defaulted to begin at the bottom left corner at origin. So you'll see the bottom left corner of the rectangle is at 0, 0, and then it goes up H dimensions or units, and with a width of W units. Circle 1. In the geometry toolbar, click circle. In the settings window for circle, locate the position section. So here's position. In the X text field, type 0.2. So now they're having us actually enter just numerical values instead of a variable, so you can do both ways. Locate the size and shape section. In the radius field, type R. So here's where we're entering a variable. It will call from the global definitions and click Build Selected. So now you'll see a circle appear inside the rectangle. Difference. In the Geometry toolbar, click Booleans and Partitions. So up here in the Geometry tab, you'll find the Booleans and Partitions button, and we want difference. So here's the difference, third one down. Find the objects to subtract subsection. Right here, objects to subtract. And so we'll click that one on. Click to select the Activate Selection toggle. Select the object C1 only, so circle 1. And you can either select it from your model builder list on the left, or you can actually select the item in the graphics window. So after selecting C1 in the Geometry toolbar, click Build All. So you can either do Build All here. This is saying in the Geometry toolbar itself, so up here in the left corner, Build All. Oh, I missed the step. Okay, so in Objects to Add, select the rectangle, Objects to Subtract, the circle, Build All. Alright, so here's the difference. This is the rectangle minus the circle. It's just a rectangle with a hole in it. Okay, and next we're on to materials. So just to get the full view of this geometry that we've built, I'm going to click the button here, Zoom Extends button. It has the it's the 1, 2, 3, 4, 5th icon over, and that will just fit the entire geometry into the frame. Alright, next we're going to define the materials. Material 1 in the Model Builder window under Component 1. So Model Builder window, Component 1, here's materials. Right-click Materials and choose Blank Material. Blank Material, so you'll see the geometry is colored purple now, showing it's selected for the material we're about to edit or add. In the Settings window for Material, locate Material Contents. So this bottom one here. In the table, enter the following settings. So our material will have a density or a variable rho of 1 and dynamic viscosity of 1e negative 3, 1 times 10 to the negative 3. And those units are kilograms per meter cubed and pascals seconds. So let's just make sure, yep, I've got my window a little compressed here to have both of them open. Let's do this. There. I've got a little more of my COMSOL window. Alright. Next, we're going to the laminar flow definitions. In the Model Builder window, under Component 1, right-click Laminar Flow SPF and choose Inlet. So we're going to right-click on the laminar flow here in this listing and click Inlet. And so you can see that it added a boundary condition tab underneath this listing for the inlet velocity, for the inlet conditions. Okay, select boundary 1 only. So under boundary selection, you can have manual will automatically be highlighted, or you can select all boundaries. We just want to do manual. Let me undo that. Okay, so manually selecting boundary 1. If you know which one it is, you can go ahead and select it, or if you hover over it, you'll see in the upper corner, I should say on the y-axis up above, I can't point to both, but it'll be right here. So you can see 1 is up there. So this is boundary 1. Click on that side and it's now highlighted in the graphics window as well as the settings boundary selection listing. We define a parabolic velocity profile using the predefined parameters. Ramp up the velocity using the previously defined step function. Append the inverse unit bracket inverse seconds to the time variable t, because the step function expects a dimensionless argument. In the settings window for inlet, locate the velocity section. So right here, in the U0 or velocity field, did it say to select this? Select or type 6 times U underscore mean, which is the variable we defined before, times Y times H minus Y over H squared times step 1 T, and we're giving it whenever you're overriding default units or units are required, like here the time step doesn't explain needs a dimensionless argument, we're putting the units inverse seconds here to cancel out the time, so that the step 1 variable will have a dimensionless unit, because the seconds from time cancels out the inverse seconds dimensions we added. All right. So it didn't say to click this, but oh, there we go. 86 that. All right, outlet 1. In the physics toolbar, click boundaries. So now we're going to the physics toolbar. That's the 6th one over on top. Or on the top toolbar, and on the top toolbar you'll find the physics tab. Click boundaries and choose outlet. Select boundary 4 only. So if we go around, we can see this is about 1, 2, 3, 4, and then the circle is broken up into 4. So boundary 4 is here on the outlet side, and you'll see the 4 populate the boundary selection listing. Where was I? Okay, so that was inlet and outlet boundaries. Now we're doing mesh. So mesh 1 in the model builder window. Here under component 1, click mesh 1. Here's component 1 and mesh 1. In the settings window for mesh, locate the physics controlled mesh section. So here's physics controlled. You can also do user controlled, but typically I'll leave this at physics controlled, and that's what the tutorial is telling us. From the element size list, choose finer. So this is where you can choose how fine or coarse your mesh is. And we're going to go with finer. Build all. Now it's going to build the mesh. The finer the mesh, the more accurate your model will be, but also the more computationally intensive it is. If you zoom in on the inlet and the cylinder, you can see the boundary layers that the physics controlled mesh gives. So if you just click the center wheel of your control on your keyboard with simultaneously zooming in with the center wheel on your mouse, or you can use the zoom in and zoom out buttons, and then if you want to reset it, you can always do the zoom extents button. So let's zoom in on the inlet, and you can see the finer mesh around the areas with greater curvature, and then it sort of spreads out into a triangular mesh or tetrahedral. What do they call this? Triangles on triangles. Right, so we'll have a greater resolution of calculations, data that it's solving for the solution at the areas where there's more change, and then less computationally intensive where You're just in a field, a flat plane. Okay, so study 1, time dependent. Step 1, in the model builder window under study 1, click step 1, time dependent. In the settings window for time dependent, so right here, locate the study settings section, and in the output times text field, type range. So here in the output times, the syntax here is going to be input, step size or increment, starting point, increment, and stopping point. So we will give it 0, 0.2, comma, stopping at 3.4, and I think it's inclusive. I'd have to look it up, but I'm pretty sure. And then, yep, there we go. So if you click on this icon, you can also enter it here, start, step, and stop in seconds. And I want to add one. So you can just click add and you'll see 2 ranges pop up. And for our second range, we're going to start at 3.5 in steps of 0.02. So we're getting finer in our increment once it hits 3.5 seconds to 7 seconds. Okay, so basically it's doing large time increments on the startup in time 0 to 3.5 seconds, and then we really want to look at the steady state. So we're getting a time dependent solution or transient solution, but we're not going so computation heavy on the startup portion of it. We're sort of skipping over the startup portion in larger steps. Okay, in the study toolbar, click the show default solver. So the study toolbar is at the top, and we want the show default solver. So this one with the 4 flags. This pops up after a second, displays the nodes and the solver sequences that are created by default. Okay, in the model builder window, expand the solution 1 node. So the sol1 node here that popped up, and then click time dependent solver 1. From the steps taken by solver list, choose intermediate. So it doesn't tell you where to go exactly. Oh no, it does. In the settings window for time dependent solver, click to expand the time stepping. So that's this section here. And you can choose your method. I don't know what these are, but you could go look in the documentation or just Google them. So we'll leave it at the default BDF for time stepping. And for the steps taken by solver, we're changing from free to intermediate. And you can also select strict or manual, and it's interpolating the solution at the end time. All right, so in the study toolbar, click compute. So this is the top left on the very top. So now it's going to compute. You can see the green progress bar on the bottom, and we'll see how long this takes. You can also see as it's progressing the number of degrees of freedom solved for, and you can look at the progress. So this will continue to iterate, so you can't really tell and then the log, if you want to look at that. So it's just going to iterate until it reaches the low enough error that the solution is accepted. Assembling matrices, solving linear system. Multi-body bola. Love you. You okay, mommy? What's wrong, buddy? All right, so we're all finished. And you can see in the graphics section, there's a graphics tab and a convergence plot. So here's the time step versus reciprocal of step size, and then the surface velocity magnitude. So now we're going to go through the results. So velocity SPF, which it has highlighted here, the surface plot of the velocity profile, click more plots. So I'm going to expand this and choose particle tracing with mass. So let's find the velocity SPF tab. Oh, at the top, the velocity SPF tab has a more plot section. So we're going to use particle tracing with mass. All right, and in the settings window for particle tracings with mass, click to expand the mass and velocity section. So that's this section here. In the mass text field, type 4 times pi, 4 times pi over 3 times 1 e negative 9 kilograms are the units. Find the initial velocity subsection. Okay, right here. And in the X component, text field, type U. In the Y component, text field, type V. Locate the particle positioning section. In the Y text field, type range. So under particle positioning and Y, we're going to put a range 0.1 and starting at 0.1 in steps of 0.05 and ending at 0.3 meters. And in the X field, type 0. Click to expand the release section. So release particles once at intervals or at times, and for this study we'll do at intervals. Select the start time checkbox and the associated text field, type 3.6. So every 3.6 seconds it will release more particles for the simulation. And the time between releases, type 0.4. 0.4 seconds between each release. Click to expand the coloring and style section. Find the line style subsection here. And from the type list, choose none. Find the point style subsection, and from the type list, choose point. In the point motion subsection, from the when particle leaves domain list, choose disappear. So let's see, when particle leaves domain, instead of stick to boundary, we're going with disappear. In the velocity SPF toolbar, click plot. So up in the left hand corner again, we'll click plot, and now you can see the little red dots representing the particles from our time release study. Next, let's see, to reproduce figure 2 and figure 3 at the lift and drag coefficients, first add an integral data set for computing the total reaction force on the cylinder. So for the next part, we'll be doing that. Integral 1 in the results toolbar, click more data sets. So up here on results, find more data sets, and now we're going to choose evaluation integral. So here's the evaluation section and integral. Alright, so we're adding an integral data set so we can compute lift and drag coefficients. Alright, so in the results toolbar, click attributes and selection. Attributes, selection. In the settings window for selection, locate the geometric entity selection. Okay, so we're already there. From the geometric entity level list, choose boundary. So instead of entire geometry, we're going to select boundary. Select boundaries 5 through 8. And so it's going to be everything in our circle here. So you can see those populate. Another way to do this, you could just do all boundaries, and then if you want to remove one, you can just highlight it in the list and click minus. and you'll see it removed from the graphic. So we've got 5 through 8 selected. 1D plot group 3 is next. In the results toolbar, click the squiggly line icon, 1D plot group. So this one here. In the settings window for 1D plot group, locate the data section. Let's see, where's data? Oh, right here. From the data set list, choose integral 1. So this integral we just added is now going to be the source data set for the pressure contour plot. Okay, and next we're adding a point graph 1. Right click the 1D plot group 3 and choose point graph. So over here, I'm going to right click from the model builder listing, and then we're going to choose point graph right here. In the settings window for point graph, locate the y-axis data section. So this section here. In the expression text field, type this expression. Got a negative react F of V times N times 2 over SPF dot rho times U underscore mean. By the way, if you make a typo, it will highlight it in red. It's for a variable you haven't defined in the global definitions. Okay, now we got it. Times quantity 2 times R, and then our units here are, oh sorry, I said times N before. This is units of newtons, not times N. Okay, units of meters squared. And then 2 close parentheses and 1 over m units. Alright, so if you click off of it and it highlights it in red, we'll just make a typo. So there's it'll tell you what's wrong, syntax expression, so you can fix it. So if it's in black, you know you entered it at least syntactically correct. Select the description checkbox. In the associated text field, type lift coefficient. So we're just describing the variable that we just entered how to calculate. In the 1D plot group 3 toolbar, click plot. Appear in the left hand corner again. This takes a second. So there's our point graph lift coefficient. In the 1D plot group 3 toolbar, click, oh I just did that. Compare the graph with that shown in figure 2. Mine's very different. Why is this so different? Finally, visualize the drag coefficient using the following steps. In the home toolbar, back to home, click add plot group and choose 1D plot group. In the settings window for 1D plot group, locate the data section. Right here. From the dataset list, choose integral 1 once again. Right click 1D plot group 4 and locate the data, right click and choose point graph. locate the y-axis data. In the expression text field, type this expression. So once again, negative reac F of U in units of newtons times 2 over SPF dot rho times U mean squared times 2 times R in units of meters squared in parentheses inverse meters units. Okay, and select the description checkbox and call it drag coefficient. In the 1D plot group 4 toolbar, click plot and compare with figure 3. We'll go up here and and look at that. Our point graph 1 looks just like the lift coefficient as a function of time, and point graph 4, it looks just like the drag coefficient as a function of time that's given in the paper. Alright, so that is the end of the tutorial, and if you walk through the paper here, it'll give you more interpretation of that analysis, that analytical, or that of this numerical solution for flow past a cylinder. So the flow of fluid behind a blunt body such as an automobile is difficult to compute due to unsteady flows. The weight behind such a body consists of unordered eddies of all sizes that create large drag on the body. In contrast, the turbulence in the thin boundary layers next to the streamlined bodies of aircraft and fish create only weak disturbances of flow. An exception to this occurs when you place a slender body at right angles to a slow flow because the eddies organize. A von Karman vortex, I don't know if I'm saying that right. Von Karman vortex street appears with a predictable frequency and involves the shedding of eddies from alternating sides. Everyday examples of this phenomenon include singing telephone wires with an automobile radio antenna vibrating in an airstream. It's important to predict the frequencies of vibrations at various fluid speeds and thereby avoid undesirable resonances between the vibrations of the solid structures and vortex shedding. To help reduce such effects, plant engineers put a spiral on the upper part of high smokestacks. The resulting variation in shape prohibits the constructive interference of the vortex elements that the structure sheds from different positions. So this model just illustrated how you can study such effects and examines unsteady, incompressible flow past a long cylinder placed in a channel at right angle on the oncoming fluid. So this model used a symmetric inlet velocity profile, and it needs some kind of asymmetry to trigger the vortex production. So this is achieved by placing the cylinder with a small offset from the center of the flow. The simulation time necessary for a periodic Freya. And then we also look at the drag and lift forces, or the coefficients of drag and lift, which are more interesting than the drag and lift forces themselves for this modeling. And these depend only on the Reynolds number and the object shape, not its size. So the coefficient of drag is defined as 2 times FD, or the force of drag, over rho, which is the fluid's density, times u mean squared, which is the mean velocity squared, times A, the projected area, or the product of thickness and diameter of the cylinder. And then for lift, coefficient of lift is 2 times the force of the lift. The coefficient of lift is equal to 2 times the lift force over the density of the fluid times the mean velocity squared times the area. And once you've gathered the results, an easy way to export these is to just take a screenshot. So you can click this icon here, quick snapshot, or Control L, and it will produce a snapshot. Where does it go? You can do the little image snapshot icon, which is the camera, and choose your preset. You can do presentation to put it into a PowerPoint and include all of these things, or don't include them if you like. You can also change the image aspect ratio. And if you want to export the clip, how do you export the clip? So the output will say where it's sending the clip, and the target can either be clipboard, so you can then just open up, say, a PowerPoint presentation and paste it there. So you can just open up a blank presentation and hit Control V, and it will, the target has already got this copied to it. Or another way you can do this is change your target to a file and what kind of format you want, PNG, JPEG, or you can do PowerPoint and just output it directly to a PowerPoint presentation. All right, so what else? You can also do a simulation to show the time progression. So let's try to do that here. This was not in the tutorial, but if you click on the contour plot you want to animate, you can also do, let's see. Oh, under the Velocity SPF tab at the top, click Animation, Player. So you can either do Player or File, and under, oh, it's already playing. So under the settings, you can choose how long it's going to play for, the number of frames. So we could increase this to, say, 50. Display each frame. You could display them for 0.1 seconds, let's do 0.2 seconds. Repeats for, say, repeat it twice, or you can do it indefinitely. Time selection, all, loop over, time, sequence, you can choose from all of these. We'll use the stored solutions default. And then target, you can just play it, the target is player, or you can target an output file. and save it as a GIF, which you can show in a presentation. So here I could save it as a demo GIF. Actually, let me call it something more. Flow over cylinder. Flow past cylinder. Alright. And then let's go ahead and output it, export. So then you can go where you saved it. Oh. So you can go to your output folder. Once it's finished, and open up your GIF so you can play it full screen. Join the velocity profile, and here's the color code over here. So the red section is going to be 2 meters per second, blue is 0. So you can see it's got a no slit boundary at the wall, and as the time increases, you can see the time expiring in the top left hand corner here. So 0 to 0 to 7 seconds. So as the time I guess I could slow it down. And then this is something you can also embed into a PowerPoint presentation. So you can put your GIF in the PowerPoint presentation, and yeah, so these you can send to people without COMSOL, and that is helpful. If you do want to create an app, there's ways to do that, but anyone who uses it would then need access to COMSOL. Okay, so this has been it for today. This has been it for the flow past the cylinder tutorial. I'm just warming up, so I'm not trying to do anything crazy where I'm generating my own ideas. I'm going off of work examples to get started. But if you have any ideas or examples that you want me to work, let me know. I'll be happy to do it. Keep in mind, I only have the COMSOL multiphysics base package, so I don't have any of the additional modules that you need. And as we continue, you'll see that for more complex solutions and solvers, you have to buy additional modules. But I can do anything with the COMSOL multiphysics. So thanks for watching, and if you enjoyed this video and want to if you enjoyed this video, please hit the like, comment, and subscribe for more COMSOL tutorials. See you next time.